I'm going to talk about quantization of hyperspectral images. It's a work I did during my second year of PhD. To talk about it, I'm going to first talk about hyperspectral images because I think not everyone is quite familiar with this kind of images. Then I will just enumerate the probabilistic distances we use to try to quantify the image. Then I will present the quantization technique we use, and I will finish with the results. So, hyperspectral images are more or less a kind of evolution of natural color images. In a sense, on natural color images, what you have a vector with just three colors, the red, the blue, and the green. So it's a vector of size 3, and it can bring interesting information. But now, thanks to hyperspectral images, we can have access to much more information, and thanks to that, we can have access to a part of the reflected light. And so what we have, it's a vector of higher dimension that gives us access to the composition of the pixel. That's quite interesting. 2 points. This kind of images can be represented as a set of vectors where each vector is a spectra, or as a set of image. It's a image at the grayscale image at a wavelength, at a special wavelength. Here we will consider that we have a set of spectra, and what we would like is a distance between spectra that would make sense. I would explain later what I mean by a distance that would make sense. Advantages of this kind of image. We have a higher dimension, as I said before. We have spectral information. We have composition information of each pixel. That may be interesting. Thanks to that, we can know that on a pixel there is water, there is soil, there is vegetation. The advantages, it's a too high dimension. Sometimes we get lost in this high dimension. We do not, each pixel in this kind of image, we have the problem that each pixel is different. And so if we have an image with 1 billion pixels, we will have 1 billion different spectra. And that's not really interesting. When we deal with grayscale images, we don't have more than 256 different colors. Here we will have 1 billion different vectors, and how can we have a distance that will make sense? Study on hyperspectral images that try to work on distance. There have been a lot of different studies. The first one, which is not a study, it's a book. But the second one and the third one and the last one are the articles. And on these 3 studies, they study different distances and try to apply it on hyperspectral images. And on the third one and the fourth one, what they did is to consider manifold learning technique in order to reduce the dimension of the data and to get a feature space where the distance will have a kind of sense. However, this kind of manifold learning technique, they needed to use some tricks because of the dimension, the spatial dimension of the data. I would like just to add that we have big images in the sense that we have a lot of pixels, and trying to use manifold learning techniques, it's not so easy in this kind of images. That's why people try to select randomly some pixel and to use manifold learning technique on pixels selected randomly, or they try to work on super pixel. Anyway, they don't work on the full image. And now, what kind of representation are we going to use on our data? We are going to consider that each pixel is a vector, but that's normal. A vector, we will have 2 vector dimension d. So d, it's the number of spectra in our image, and we can represent this vector by the probability mass function, written px and py. Moreover, we will consider that on each image, what we have a finite number of material and also a finite number of class. We may have some ground truth information, so we know we know that some pixels belong to this class and some other belong to another class. That's a kind of important point in order to check that a distance makes sense. And now, what do we want for a distance? I have illustrated here kind of as an illustration. I've just considered 3 clusters of an hyperspectral images, and then on each of these 3 clusters, I calculated the barycenter, and then on each axis, I calculate the distance of each of the points of the 3 clusters to the barycenter, according to 2 different norms. What we can see that we would like that a good distance. What is a good distance now? We can see that a good distance would be a distance that would bring spectra that are on the same cluster near to the barycenter of the cluster we consider, and spectra that does not belong to the same cluster far away. And with the norm 2, what we get that the cluster blue and the cluster green are more or less mixed, and that's not at all useful, whereas with callback divergence, I'm also using the divergence. With the callback divergence, what we get is that all the clusters are a bit far away from each other. Oops, sorry. So our first goal would be to find a distance and to try to use different distances that are already used on hyperspectral images, and also other Fisher metric distance that can be used, and to see if they would make sense on the case of hyperspectral images, and also to try to quantize at the end our hyperspectral images to reduce the number of spectra, so that we will have more, in the sense, the image will be more easily understandable. So, distance, we use different distance. We first use norm 2, Euclidean norm. We also use the spherical distance that is quite used in Fisher-Rao distance. It corresponds to a kind of model of data. This spherical distance is also linked with a distance that is classically used in hyperspectral images, which is the sum. That's why it's also interesting. And at the end, we also use different Rayleigh divergence that could also, in a way, bring interesting invariants that may help us to separate the data. We use also the analogy distance. The definition is just here. And Earth-mover distance. The problem with the Earth-mover distance is the calculation. I try to use the classical Earth-mover distance. The problem is that I simplify the cost. I use the cost defined with C1, where finally the Earth-mover distance happens to be just a norm 1 between cumulative distribution function. But the problem is that this kind of cost, there is no really justification for this cost. In the case of hyperspectral images, I could have worked with another cost. However, if you have to calculate the Earth-mover distance between 1 billion pixels, it would take too much time. That's why I didn't select another kind of cost. And then I try to use also the fast Earth-mover distance, where the cost function is a bit different. It's the one implemented by Michel Elad. And the result, I will show it later. Anyway, the quantization technique we use, we would like also that during the quantization, what we work with is images. So we would like that spatial information should be taken into consideration when we do the quantization. To do that, we use connected component, alpha connected component, where in a way, 2 pixels belong to the same alpha connected component if there is a path between the 2 pixels, and if each time the distance between the pixel and the path are less than or equal to alpha. And it brings this kind of images where each color is a different alpha connected component. But instead of using the alpha connected component at the pixel level, we selected to use it on a graph. And what we did, we started with this image, the image in A, and this one. And what we did is to try to calculate a superpixel representation of this image. Then on each superpixel, we calculated the barycenter, and then we represented the graph where the weight between two nodes of the graph, so where each node would be a superpixel, and where the weight is the difference between two barycenter of the two superpixels. To calculate the barycenter is the formula, and the result, to evaluate the classification, what we did is to use usual classification evaluation techniques that are current in hyperspectral images. So we use what they call the overall accuracy and the average accuracy. It's a kind of accuracy between the different classes. It's a kind of way to see the accuracy when we have a multi-class problem. And we also use the rank, which is a way to see how well is in machine learning technique. What they do sometimes, they try to see if among the if you have to classify one thing, they would among a lot of different classes, they would say when do you consider that this thing is of this class, and the rank it's when I found a good class for each spectra, and I divide by the number of class. So the rank, if it's too high, it means that it's really bad, because it means that it found the class too late, and if it's quite small, it means that it's really good, and that's the rank. The average and the overall accuracy are accuracy measures, so they need to be really high to be quite good. And the SNR, it's the SNR of the quantization technique. And what we get up to all that thing is that at the end, in perspective images, we don't have a lot of different images, so I use just 2 images, but that's quite common on this kind of data, because we don't have ground truth for a lot of images. And I use the 2 most popular images. And on this one, what we can see is that callback divergence and K2 present quite good results. And on this one, it's the K2 distance represent quite good results. And then I just apply the quantization technique I just presented on these images. So in small a, you will see the image. I just selected 3 channels so that we get a false RGB image. Normally, you have 200 channels, but you will never be able to see it. So yeah, I selected just 3 channels. And in B, C, D, and E, you will get the different quantization according to different distances. And the same for another image. And thank you for your attention.
Thank you very much for your talk. Are there any questions? Did I understand correctly that at this point you do not do a prior dimensionality reduction? So how many wavelength bands are you using?
I have about 100 wavelengths, 100 or 200 wavelengths. I selected to do not do dimensionality reduction. I could have done PCA, but PCA was already studied, and I will do a study where I compare dimensionality reduction with other kind of techniques. But I wanted first to select a distance without any dimensionality reduction before.
Okay, because I assume not all the wavelength bands are equally important in terms of information regarding what you want to get out of it.
Definitely, and there is a lot of correlation between different bands. But the thing is that all the technique of dimensional reduction cannot be applied on this kind of data. And only some simple one can be applied. And so I cannot use manifold learning techniques, and that's quite sad.
Okay, thank you. Any more questions?
Thanks. In fact, have you a physical reason, justification to look at the normalization of the spectral representation?
The normalization, in a way, it makes sense since thanks to the normalization, what we get that it's illumination, it's invariant to the illumination, to the change of illumination. If we increase by a factor alpha the illumination, thanks to the normalization, this factor alpha would disappear. And so two different vectors that just change because of this value of alpha that I multiply all the vector would be exactly the same.
Yes, but we have the problem with the noise when you have no level, something without. If you don't have a specific region of your spectral band with a specific form, if you have a low level for all the band,
yes.
Okay, the normalization increase the noise, no?
The normalization would increase the noise,
but perhaps it's not the case for this kind of data. I don't know.
I use the normalization to be able also to use Earth moon resistance, because I needed to have that all the vectors should have the same weight sum, and at the end I needed normalization to use some distances. But I totally get your point that I would increase the level of some noise, but in a way, a solution I could have done, I didn't do, would be to remove there are some wavelengths that brings only noise, but they are not so much.
Okay, and the last question. I see that you have used Mahalanobis distance.
Yes.
Yeah, but on what you estimate the covariance
I
matrices?
estimate the covariance on the full data. One covariance
along the spectral band?
Exactly. It's
Okay.
a covariance of it's a covariance matrix of Zeiss, the number of the spectra, and then I just calculate the Mahalanobis difference between one spectra and one spectra.
Thank you again. I think it's okay. So this is the end of the session.